Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about DeMorgans theorem, so let's get started. Alright everybody, so let's draw some gates, shall we? Why don't you draw this gate while I'm drawing it, alright? It might help you in your understanding of what we're about to discuss. Now, the inputs on this AND gate with an inverted output are A, B, and Y. Okay? So if I were to ask you, what is the expression on this? I believe you would come up with A. Actually, I should do it in a more appropriate way, shouldn't I? So we'll just say Y equals A dot B bar. Alright? Now we've discussed the bar, so this should make sense to you, right? Now, I have another gate for you. Now let's look at this one. This is going to be A. That's going to be B. This is an OR gate. With two inverting bubbles at the beginning, right? So we have Y. Y is going to equal A bar or B bar. Get it? Let's draw the truth table, shall we? Draw this line nice and straight for you. There we go. So the truth table is what? 0, 0, 1, 0, 0, 1, 1, 1. So I'm going to call this side right here. This is going to be number 1, and this side, this gate, is number 1. And this gate I'm just going to call number 2. So let's just look at Y for number 1, shall we? If both are 0, this is 0 right here, and this is 0 right here, your output is going to be what? Well, it's going to be a 1, isn't it? Because it's inverted. Now, let's do another one, shall we? If we have a 0, 1 or 1, 0, it's not going to make a difference, is it? That's going to be a 1, and that's going to be a 1. But if we have a 1, 1 coming in, that means with this inverter bubble, that's going to be a 0, right? So that's your truth table for your number 1 gate, all right? Let's do the truth table for the other one, shall we? So if we have this is what we're doing right here, A and B. If A and B are both 0 and you invert them, that means they're both 1s. That means Y will be a 1, won't it? Same thing here with 0, 1 or 1, 0. Only one of them has to be a 1, right? So this would be the same. Now, if they're both 1s coming in, they both obviously are inverted to 0, so the output is 0. Now, what do you notice about those truth tables? They're the same, aren't they? Both gates result in the same logic. So what we're going to be talking about now is DeMorgans theorem. All right? Basically, if you notice, let me get rid of this here. This delete. Okay, we deleted it. Let's just move them over like that, shall we? So if you notice, both of those gates deliver the same truth table, don't they? When I say gate expressions, I should say an AND gate with an inverted output gives the same value as an OR gate with two inverted inputs, doesn't it? Okay. Now, basically, there's a method to building an equivalent gate with another gate. Okay? First, you look at the general shape of the gate. Is it an AND? This is an AND gate, right? So we have an AND gate here, and we have an OR gate here, all right? Now, then you look at the inputs. Here, A and B are not inverted. In this case, I'm going to say not inverted. And over here, they're inverted, aren't they? And what is the output? That's going to be input. So let me put that in here. Okay, one is not inverted, one is inverted, right? And let's look at the output. The output here, this one's inverted, isn't it? And this, the output, is not inverted. Alright? Basically, there are those are the three items you have to look at. It's basically the type of gate, whether it's an AND or an OR, the inputs, right, or the outputs, and the outputs, okay? Three things. Here's another gate. Let's just do this for an example, right? That doesn't look too pretty, does it? This is an OR gate, right? It has an inverted output here and one of the input gates, right? So let's draw first thing, you're going to have to change gates. So this was an OR gate, so now we're going to have an AND gate. Got it? That's the first thing. Now, A and B, right? B was inverted, A is not. Well, if this is A and this is B, let's change this, shall we? In this case, you're going to have A inverted and B is not going to be inverted, and then your output's not going to be inverted, is it? Right? There's no inverter bubble right there, right? Why don't we do a truth table, okay, for these gates, and we'll just see. So we'll have an A, we'll have a B, and we'll have a Y. Now let's call this one 1 over here, and we'll call this over here 2, alright? So we'll call this Y1 and Y2, okay? So here we go. Let's just go through and draw it. This is a way to check your work. Whenever you do something, you want to check your work, okay? You want 0, 0, 1, 0, 0, 1, 1, 1, okay? Now let's take a look at it. Let's do this first gate. If they're both 0, that means you have a 0 here coming in, and you have a 0 and it's inverted to a 1. So the OR gate is a 1, 0, right? So with a 1, 0, the output's going to be a 1, but it's inverted by this bubble, isn't it? So it's going to be a 0, isn't it? Now, let's do the next one. A is going to be 0, B is going to be a 1. So it's going to be 0 coming in here. This 1 is going to be inverted to a 0, right? So you have a 0, 0 coming into an OR gate. The OR gate's going to output a 0, which is going to be inverted to a 1. Get it? Here's your 1. So let's do the next one. A is 1. B is 0. So this would be a 1 coming into your OR gate right here. Your 1, 0. This 0 is going to be inverted to a 1. So you have a 1, 1 coming into your OR gate, which would put a 1 out of your OR gate, which then is inverted by this inverter bubble, right? So it would be a 0, wouldn't it? Finally, 1, 1. Well, you have a 1 in your A input over here, which would be a 1, right? And then your B, the 1 would be inverted to a 0, so it would be a 1, 0. In an OR gate, that would output a 1, which is inverted to a 0 with that inverter bubble. Here it is. All right. Now let's do the same, check it with Y2, what we just wrote, all right? A is 0, B is 0. Well, if one of these inputs is a 0, you know the output's going to be a 0, right? So that's going to be a 0. Makes sense? The next one. A is 0, B is 1. You have a 1, 1, right? If this input is a 0, it's going to be inverted by that inverter bubble, so you're going to have a 1 coming in, right? And this one's already a 1 because it's 0, 1. B is 1, A is 0, I should say. So you have two 1s. It's going to output a 1, isn't it? Now, let's try it the other way. B is a 0, right? A is a 1. Well, since one of the inputs in the AND gate is a 0, you know the output's going to be a 0, right? So that's going to be a 0. Finally, we have a 1, 1. Well, again, with A being 1, it's inverted to a 0. Since one of the inputs on an AND gate is a 0, the output's going to be a 0. So, do you see this? It's the same. So basically, it's the same, right? These two gates give the same truth table. So if you're building a circuit and you only have AND gates, or you only have OR gates, you know, you have available OR gates, you can make an AND gate out of an OR gate and vice versa, okay? So let's go over again the 3 methods for this, all right? So, when converting, first, change gates, okay? So this means an AND goes to an OR an OR goes to an AND. Got it? 2. Complement inputs. I'm just going to put inputs. Now I think you understand what that means. So if the input on your first gate, okay, not inverted, then you're going to what? Invert on your other gate. And if they are inverted, then you're going to not invert them. Alright, and the same thing goes for your outputs. It's exactly the same thing, right? So if it's not inverted, see why I'm having problems writing this today. My mind's moving too fast. Not inverted, you're going to invert. And if it's inverted, you're going to not invert. Got it? So that pretty much says what has to happen to utilize DeMorgans theorem to convert gates. Alright? Now, it doesn't matter how many inputs you have either. So if you have a gate, and let's just increase these. Let's do one more example. You have a gate. Suppose you have a 3-input gate here. I have an AND gate. It's not inverted. And let's just say you have one of these inverted. This is A, B, C, right? If I were to have you write the DeMorgans equivalent to it, right? First thing, what's the gate? Gate's going to be an OR gate. Okay? Your out, well, let's do the inputs first. Inputs, you're going to have not inverted, then you're going to have an inverted, and then you're going to have an inverted. This is A, B, C, and your output is going to be inverted. Get it? There is your gate. You could have 5, 6, 7 inputs. It doesn't matter. Just remember, if the input is inverted, then don't invert it. Then uninvert it. If the input is not inverted, then you're going to have to invert it in your output. And the same in your second gate. Your output is the same thing. So if it's not an inverted output, you're going to have an inverted output. Okay? If it is an inverted output, if this, for example, had an output bubble there, then when we wrote the new gate, we would simply uninvert it, which means you don't have an inverter bubble there. All right. I hope this has been helpful to you. See you soon. Alright, so next in this video, I would really like to go over logic enable. And you also could actually continue this with disable too, if you're going to enable something or disable something, right? So let me ask you a question. To enable a gate, what do you think that means? Well, think of it, you can think of it to turn something on, right? Or to let something pass through. It's kind of like a bridge, you know. You could lower the bridge. If it's a drawbridge, you lower it so people could cross, right? And to disable a gate, it means you can do just the opposite, right? Turn off, or let me say not pass through, right? So let's think about it, right? Suppose you have an AND gate here, right? Okay. Here's input. Now, A, B, and Y, right? Now let's just draw these signals, shall we? If we have this be A, this be B, and this be Y, okay? Now, suppose we have B be high and then be low. This is a 1, and this is a 0 over here, right? Now suppose A oscillates, it changes, right? So it's low, then high, then low, then high, then low. Now suppose these are at the same time, okay? What would you expect Y to do? Well, remember, truth table, right? Both A and B have to be 1 for it to be high, right? Otherwise, it will be low. Got it? So, let me do this here. So if we're looking at Y, it would start off, we have a 0. This is a 0 right here at this one. This point, that's a 0. This is a 1, okay? And it just repeats. So we'd have a 0 on A. I'm just drawing these timelines down, right? So if you have a 0 on A and a 1 on B, your output would be a 0, right? So just write a 0 right here for you. Now, at this point in time, the next stage, I'm drawing these lines down here for you, you have a 1 on A and a 1 on B, right? That means it would come up and it would be a 1, wouldn't it? Got it? The next stage, it would just repeat. Since A is 0, Y would be 0, right? Let me bring that in and neaten that up just a little bit for you, okay? There we go. Now we come up, bring it across, because we have a 1 and a 0. It's the same thing, get it? Come across. Pretty close there. Let me just clean that up for you. So I think we got that understood, right? The thing is, if you look at this now, the signal A passed through this gate B to Y, because the output Y is the same as the input A, isn't it? So this part from here to here, when B is high, right here, that gate is enabled, isn't it? Got it? Now, what happens when B is low? That's in this next part, from say here to here, right? So what is the output Y going to be? Y is simply going to be 0, isn't it? All the way along here, right? It's going to be 0. That's because the AND gate requires a 1, all 1s on the inputs for it to be 1 on the output. And since one of the inputs is 0, B is 0, it's always going to be 0. This would be disabled. Termed disabled, I should say. Get it? Now, let's try something else, shall we? Let's do this here. So, Let's do the same thing for a OR gate, shall we? Gate. Now you can do this for any gate you want, right? The point I'm trying to make here about enable or disable is allowing the signal to go through, all right? So if a logic signal is able to go through unaltered, it's enabled, okay? So the thing I want to talk about now is disable. And the examples we've had, if it's disabled, it's a logic. We've seen that it's been a logic low, but the gate can also be disabled with it being a logic high, okay? So let's try this. A, B, and Y. And we'll say A is gonna, let's say low, high, low, high. Let's just keep going here. Now B. Well, we can make B low for the first part, and at this point we'll make it go high. Alright? So what's Y gonna do? Remember, this is a 0 at this point. A is 0, and B is gonna be a 0 here, right? So 0, 0 means Y is gonna be low, right? First part. And let's just bring down a dotted line. When you're doing problems like this, a lot of times it's good just to bring down these dotted lines because you can see where the transitions will take place. It'll keep your drawings in order. Okay. Now, what do we have here? We have a 1 and a 0. What's that going to be? For an OR gate, that would be a 1, right? There it is. And then we're going to repeat. We have a 0, 0. So we're going to repeat this, isn't it? Now, obviously, you can see from this point to this point, this gate is enabled, isn't it? It's just allowing the signal to go through, right? Because the signal here for Y is identical to the signal for A, right? Now, what happens when B goes high? When B goes high, the output is going to be a 1 always, right? Because remember, with an OR gate, it's A or B. But in this area, this is disabled. Got it? This is disabled here, and this is enabled. But you notice this is disabled high. When we used the AND gate, it was disabled low. But its objective was the same. It stopped the signal from going through, so it was not enabled. Okay? That's really what I wanted to show you about these gates. Now there's one other thing that's important about another gate. Now tell me, what is this? What does this represent? Well, many of you have seen this as an inverter, right? So sometimes they're called buffers as well. Okay, but that's an inverter because it's going to take a high and make it a low, or a low and make it a high. You can also have this. These are buffers. All right. Now, this obviously inverts the signal. The top one inverts the signal here. This one does not because there's no inverter bubble. But let me show you the difference between these and as far as what we're talking about, okay? What we're talking about called a Tristate Buffer. Tristate buffers have three inputs to it, right? Actually, two inputs and an output, but this is your input, this is your output, and this is your, I'm going to call it your control. This is how you turn it on or off. This is termed your output enable. Okay? So what does that mean? That means that if you have a signal coming in, if your input looks like this, your OE, and then your out, okay? So if your input's going high, then low, then high, then low, and your output enable is low, let's just say this is a 0 here, okay? That, by the way, your output enable, it's active low. That's what that bar means, okay? So when it's low, that means your output enable is on. So then, if we look at the output, it's simply going to be, got it? That's basically what we're saying here, okay? Now, when that output enable goes to a 1, like this, your input obviously can keep coming in like this, it doesn't matter. This point, it's called high Z. It's high resistance. It's like it's disconnected. Think of it as a switch. Okay? So that's just a switch right there. I just tried to draw a switch for you. Those little circles are not inverter. I'll make them, fill them in. I don't want to confuse you. Those are not to be confused with inverter bubbles. They're not. They're just, that's a switch. So when the output enable is high, which means it's not active, that means it's been basically disconnected from the circuit. Okay? So that's why we call it high Z. All right? Now, the thing is, for this other side, it's the same thing, okay? There you go. So we'll come in. Here's your output enable. We'll go low, and then we'll go high, okay? And that's what you're out. Well, if your output enable is low, it's just simply going to repeat the signal coming in. It's not inverted, get it? But when you go high, all right, when this goes high again, you're at high Z. And it's the same as having a switch there. So when your output enable is high, because again, this is active low, because you have a bar over it. And you can tell when output enable is low, that's when your output has a signal, right? But when your output is high, you're in high Z mode. It's like it's not connected. These things are used when you connect circuitry to a bus. You don't want to load down the bus if that piece of circuitry is not in use at that time, okay? Now, they have different chips, obviously, with these buffers in them. They come in groups of 8 or 16, and they have different enables. But that's the basic function of them, okay? You're going to have a pin which is an enable, and you're going to either enable or disable that tri-state buffer, which is going to allow the signal to either go through or not go through. All right, everyone. I hope that has been helpful to you, and I will see you again soon. Thank you. Bye-bye.